Hi, I'm Dale, and I'm going to show you in detail how Bitwig's Harmonize device operates internally. In an earlier video, I described how Harmonize works as seen from the outside. In this video, I'm going to give the inside view, the actual steps that Harmonize follows whenever it receives a note message from its input or from its live harmony source. It's a clever, elegant idea. I'm not going to show any code. Heck, I'm not even going to show Bitwig. But I will show what's called a theory of operation, a detailed model of what the code does. And I'll do my best to describe it in simple, non-technical language in a way that makes Harmonize's internal operation clear and understandable, all the way from the big idea of the device down to the tiniest detail. The big idea of Harmonize is this. You tell it where to find some harmony, and you play some notes, and it makes the notes move along with the harmony. That's a really useful, really musical idea. To do that, Harmonize responds to the messages it receives from two sources, the device's input and the live harmony source. Everything Harmonize does is in response to one of these messages. Until a message arrives, Harmonize sits idle and waits for some work to do. Harmonize responds to two kinds of messages from the live harmony source, note-on messages and note-off messages. Whenever Harmonize receives one of these messages, it records the change in the harmony, summarizes the harmony, and plans how to respond in the future to messages that arrive at its input. Harmonize responds to three kinds of messages from its input. When a note-on message arrives at its input, Harmonize implements the plan it created based on the harmony to decide what note to play. The other two input messages are note-off and what I'll call note-update. When one of these messages arrives, Harmonize redirects the message to the corresponding output note. Now let's look in detail at how Harmonize responds to each kind of message. Whenever Harmonize receives a note-on or note-off message from the live harmony source, it summarizes the harmony and builds a plan for how to harmonize input notes. Step 1 is to record the state of the harmony. Harmonize keeps track of the entire state of the harmony by using a table with 128 rows, one row for each possible MIDI note number from C-2, note number 0, to G8, note number 127. The row for a given note indicates whether the note is active or inactive in the harmony. Initially, before the first message has arrived, every note is inactive, which I'll represent by dimming the notes. Whenever a note-on or note-off message arrives from the live harmony source, Harmonize first updates the table to record the new state of the note. A note-on message leaves the note active. A note-off message leaves it inactive. After Harmonize updates this table, the rest of the steps are identical for both note-on and note-off messages. Suppose Harmonize has received a series of note-on messages from the harmony and has fully completed all of the steps for those notes. Now, a new note-on message arrives. As always, the first step is to update the active harmony table. Step 2 is to identify the root note of the chord. Harmonize uses this information in the following step to help summarize the harmony, and also later to transpose the input notes. To identify the root note, Harmonize simply scans the table from the lowest note to the highest until it finds a note that's active, and calls that the root. Harmonize has no concept of chord inversions. It doesn't do any kind of sophisticated analysis to identify the type of chord and pick the root note from that. It simply finds the lowest active note and calls that the root. With this harmony, the lowest note, the root note, is F3. Once Harmonize identifies the root note, it then reduces the note to its pitch class. Every note has a pitch class. Think of the pitch class as the name of the note without regard to the octave of the note. The pitch class of F3 is F. Harmonize records the pitch class using integer notation, which represents each pitch class as a number from 0 to 11. The number indicates how far the note is up from C, measured in semitones. F is 5 semitones up from C, so the pitch class of our root note, F3, is 5. From this moment on, Harmonize no longer cares about the octave of the root note. It cares only about the pitch class. There's one additional detail that will matter later. Before Harmonize scans the active notes to find the root, it first forgets any root note that it might have identified earlier. So there's a very brief moment where Harmonize has forgotten the old root, but hasn't yet scanned far enough to find the new one. This creates a special circumstance that we'll have to deal with later. Step 3 is to identify which chord factors are active in the harmony. Each note in a chord has a chord factor. The chord factor of a note is its position in the chord, that is, the distance of its pitch class up from the root pitch class. Here again, Harmonize uses integer notation, representing each chord factor as a number from 0 to 11, measuring the distance in semitones. Harmonize identifies the chord factors so that in the next step, it can build a plan for how to harmonize the input notes. To identify the active chord factors, Harmonize first creates a table with 12 rows, one for each possible chord factor, and initially marks each chord factor as inactive. It then scans the entire state of the harmony, and whenever it finds an active note, it identifies the note's chord factor and marks that chord factor as active. Let's walk through our active notes. The chord factor of the root is always 0 because the root is always 0 semitones from the root. If there's any harmony playing at all, chord factor 0 will always be active. The next active note is A3. Its pitch class is A, which is 4 semitones above the root pitch class F. So chord factor 4 is active. The next note is C4, pitch class C, 7 semitones above F. Chord factor 7 is active. E4, pitch class E, is 11 semitones above the root pitch class. But now what about G4? G4 is 14 semitones above F3, but chord factors only go up to 11. Remember when I said that Harmonize no longer cares about the octave of the root note? Well, it never cares about the octave of any other note in the harmony. It cares only about their pitch classes. So we'll ignore the octave numbers and ask, how far is G above F? 2 semitones. So with this harmony, the chord factor of this G4 note is 2. In step 4, the final step, Harmonize prepares a harmonization plan, a plan for how to convert the scale degree of every possible input note to a chord factor that fits the harmony. The scale degree of a note is its position in the scale, its distance up from the tonic of the scale. There are 12 possible scale degrees, and Harmonize numbers them, you guessed it, from 0 to 11. Scale degrees, chord factors, and pitch classes are all similar ideas. They identify a note's position in some octave. The difference is whether we're identifying the note's position in a scale, in a chord, or on a keyboard. We now know which chord factors are active in the harmony. Harmonize uses that information to build its harmonization plan. To do that, Harmonize considers each possible scale degree and applies 4 rules in priority order to identify the best chord factor to play. The first possible scale degree is 0, the tonic of the scale. Rule 1 says, if the chord factor with the same number as the scale degree is active in the harmony, play that chord factor. We're working on scale degree 0, so we'll check chord factor 0. Is chord factor 0 playing in the harmony? Yes, it's the root of the chord. So with this harmony, whenever a note with scale degree 0 arrives at the input, Harmonize will play chord factor 0. Rule 1 handles the best possible case. If you're trying to play a note that conforms to the harmony, you can't do better than to play a chord factor that is already playing in the harmony. Now scale degree 1, the minor second of the scale. We'll try the same rule. Is chord factor 1 active in the harmony? No, so our first rule doesn't apply. Rule 2 says, if the chord factor below the scale degree is active in the harmony, play that. The scale degree is 1. The chord factor below that is 0. Is chord factor 0 active in the harmony? Yes. So if a note with scale degree 1 comes in, play chord factor 0. Rules 1 and 2 also handle scale degrees 2 through 5. They don't handle scale degree 6. Chord factor 6 is not active, and neither is the chord factor below it. We need another rule. Rule 3 says, if the chord factor above the scale degree is active in the harmony, play that. Chord factor 7 is active, so that's the one we'll play. The idea behind rules 2 and 3 is to avoid playing notes that clash with the harmony. As far as Harmonize is concerned, a note clashes with the harmony if the nearest active chord factor is one semitone away, one semitone above or below. Whenever a note would clash, Rule 2 or 3 detects it and plays an already active chord factor instead. When there are two active chord factors to choose from, one above and one below, Rule 2 wins because it comes first, and so Harmonize prefers the chord factor below. Scale degrees 7 and 8 are handled by Rules 1 and 2. Scale degree 9 presents a new scenario. Is chord factor 9 active in the harmony? No. The chord factors below or above? Also inactive. Rule 4, the last rule, says, play the chord factor with the same number as the scale degree. Chord factor 9 isn't active in the harmony, but it also doesn't clash with the note above or below. If it doesn't clash, that's good enough for Harmonize. So play chord factor 9. Rule 4 is the only way that Harmonize will play a note with a chord factor that isn't active in the harmony. Rules 1 and 2 handle scale degrees 10 and 11, and we're done building the plan. What if chord factor 11 were not active in the harmony? What happens if a note comes in at scale degree 11? It turns out that a note 12 semitones above the root has the same chord factor as the root, so the chord factor above 11 is 0. If an input note arrives 11 semitones above the tonic of the scale, Rule 3 would pick the chord factor above 11, chord factor 0. When Harmonize finishes processing a note on or note off message from the harmony, it knows three things that it will use later: which notes are active in the harmony and which are inactive, the root pitch class, the pitch class of the lowest active note in the harmony, and a plan for how to transform each incoming scale degree to the best chord factor to play. This harmonization plan is the heart of Harmonize. Everything else that Harmonize does is in support of applying this magical musical transformation. This plan tells us how to transpose any input note from its position in the scale to a harmonically pleasing note at or near that same position in the chord. When the documentation says that Harmonize transposes notes and conforms them to the harmony, it's this harmonization plan that does almost all of the work. With this harmonization plan in hand, Harmonize is now ready to make the input notes dance with the harmony. Let's see how Harmonize uses its harmonization plan when it receives a note on message at its input. Before a message arrives, Harmonize sits idle waiting for something to do. Now a message arrives at the input, informing Harmonize that the note D3 just came on. Harmonize responds to each note on message by performing three steps: choose the best note to play the note, and record that it mapped that input note to that output note. First, it chooses the best output note to play. There's a lot of detail in this step, including a nasty error. For now, I'm going to skip all of that, and I'll come back to it later. Let's just pretend that Harmonize has chosen to play C3. The note on message includes more information than just the note number. It also identifies the velocity of the note and the MIDI channel on which the message was sent. Harmonize wants to preserve this other information, so it simply replaces the input note number with the output note number, leaves everything else the same, and forwards the message through its output to the devices that follow. As a result, the output note plays at the same velocity and on the same MIDI channel as the input note. Step 3 is for Harmonize to record the state of the input note. To do that, Harmonize maintains a table with a row for every possible input note. Initially, every input note is inactive. After Harmonize sends a note on message out, it records that the input note, in this case D3, is now active. And it records that when D3 came on, Harmonize played C3 instead. Harmonize will need this information later when it handles note update and note off messages. Now let's take a look at that doozy of a first step, choosing the best note to play. Suppose we've set the incoming note key parameter to tell Harmonize that the tonic of our scale is G. Our note on message for D3 has just arrived. The heart of this step is to apply the current harmonization plan, the one that Harmonize created the last time the harmony changed. Remember that the harmonization plan tells us how to translate from any given scale degree to the best chord factor to play. In order to apply the plan, we need to know the scale degree of the input note. Once we know the scale degree, we'll apply the plan to identify the best chord factor. Then we'll translate that chord factor to an actual note. To do that, we'll need another bit of information which I'll call the octave tonic note. I'll start with that. The octave tonic note is the lowest note in the octave that contains the input note. Harmonize needs this information to achieve an unstated goal, a goal that isn't mentioned in the documentation. Harmonize wants to play the output note in the same octave as the input note. To do that, it needs to know the note where the octave starts. Let's find that note. To illustrate, I'll show our input note in this table. Harmonize doesn't actually create a table like this. This is just for illustration. Our input note is D3. You might think that the lowest note in that octave is C3, but Harmonize doesn't divide octaves at C. Instead, it considers each octave to start at the tonic of our scale, that is, at a note that matches the incoming note key. The octave that contains the input note starts not at C3, but at G2, so our octave tonic note is G2. Now we can find the scale degree of the input note. The scale degree of a note is its distance from the tonic of the scale. How far is D3 above the tonic? We can simply count up from the octave tonic note. D3 is 7 semitones above G2, so its scale degree is 7. Now we've identified the input scale degree and the octave tonic note. Earlier, we identified the root pitch class and built our harmonization plan. We're ready to apply all of this information to find the best note to play, the output note. As I walk through this process, see if you can spot the error that Harmonize makes. First, Harmonize translates the scale degree of the input note to the best chord factor to play. All of the work that Harmonize did to analyze and summarize the harmony makes this step very simple. All we have to do is look up the scale degree in the harmonization plan and find the associated chord factor. For scale degree 7, the best chord factor to play is 7. That is, the best note to play is 7 semitones above the root of the chord. I want to pause here for a moment of appreciation. We've just done something that's both subtle and magical. Subtle because it looks as if we've done nothing more than possibly shift a number up or down by 1. But there's magic here too. We've just transposed the note from its position in the scale to a position in the chord. That is, we've transposed the note based on the harmony. Not only that, we've also adjusted the note to make sure that it fits with the harmony. And we've done all that with a single lookup. I think that's pretty magical. We now know the chord factor to play. We need to translate that to a note that has two qualities. It's at this position in the chord, and it's in the same octave as the original note. Harmonize does that through two computations. First, it adds the selected chord factor to the pitch class of the root note of the chord. This gives us the pitch class of the output note, pitch class 12. But wait, that's too high. Pitch classes only go up to 11. If a pitch class is too high, subtract 12 until it's in the right range. If we subtract 12, we get pitch class 0. Remember that the pitch class of a note represents how far it is above C. We've just learned that the output note will be 0 semitones above C. We're going to play some C note. Finally, Harmonize adds that pitch class to the octave tonic note to determine what note number to play. The octave tonic note is G2. Adding our pitch class 0 gives us G2, and that's the output note that Harmonize will play. Wait a minute. A moment ago we said we wanted to play a C. Now we're playing a G2. What the heck happened? Did you spot the error? the developers didn't. It's right here where Harmonize adds the chord factor to the pitch class of the root note. That seems like a reasonable thing to do. It tells us the pitch class of the note to play. But then we need to convert that pitch class to a note number that's in the same octave as the input note. How would we do that? Clearly, adding the octave tonic note isn't right. That gives us a G. This may not look like much of a problem. After all, the output note, G2, is in the key of G, and it doesn't clash with the harmony. But that's just a coincidence based on my particular choices for the harmony in the input note. If you experiment with different keys and you set incoming note key as the documentation encourages you to do, you'll quickly find that Harmonize plays many notes that actively clash with the harmony. Specifically, every output note has a pitch class that's too high, and the overshoot is equal to the value of the incoming note key. Fortunately, there is a way to tame Harmonize and make it work as intended in every key. For that workaround, see my earlier video, Bitwig Harmonize Repair Manual. How should Harmonize determine the output note? Let's start over. From the calculations we've done so far, we know the chord factor we want to play, we know the pitch class of the root note, and we know the lowest note of the octave that contains the input note. And from the incoming note key parameter, we know the pitch class of the tonic of our scale. Let's work backward from the input note. We'll start with Harmonize's unstated goal. Harmonize wants to play the output note in the same octave as the input note. That octave starts at the octave tonic note. The output note then will have to be some distance from 0 to 11 semitones above the octave tonic note. That distance is the scale degree of the output note. If we knew the scale degree of the output note, we could add that to the octave tonic note and find the correct output note. How can we find the output scale degree? So far, all we know about the output note is its chord factor, that is, how far the note will be above the root of the chord. If we knew how far the root of the chord was above the tonic, that is, if we knew the scale degree of the root note, we could add that to the chord factor of the output note to find the scale degree of the output note. So now we need the root scale degree. We already know the pitch class of the root note. We'd like to know its scale degree, how far it is above the tonic. We can find that by subtracting the pitch class of the tonic, and that's exactly what the incoming note key tells us. If we subtract the incoming note key from the pitch class of the root note, we get the scale degree of the root note. Now all that's left is to do the arithmetic. First, we'll subtract the value of the incoming note key 7 from the root pitch class 5. That gives us a root scale degree of -2. We need a number between 0 and 11, so we'll add an octave by adding 12 semitones. The root scale degree is 10. Fun fact, Harmonize actually computes the root scale degree. It uses it in one of the special cases I'll describe in a moment. Unfortunately, the developers forgot to use it here. Next, we'll add the root scale degree to the output chord factor to get the output scale degree. 10 plus 7 is 17. Again, we need a number between 0 and 11, so we'll subtract an octave by subtracting 12. The output scale degree is 5. Finally, we'll add that to our octave tonic note to get the output note. 5 semitones above G2 is C3. Our output note, the correct output note, is C3. If Harmonize operated correctly, which it does not, it would play C3. That's nearly everything there is to know about how Harmonize responds and how it's supposed to respond to a note-on message at its input. Everything I've described so far is what happens when Harmonize has enough information about the harmony to transpose and conform the input notes. What if it doesn't have enough information? There are two circumstances where that can happen, two special cases. The first is when Harmonize has not identified a root pitch class. One way this can happen is if the harmony isn't playing any notes. If there are no notes, then there's no root note. This can also happen potentially if Harmonize is doing two things at once. Specifically, if one part of Harmonize is responding to this note-on message, while at the same time another part is responding to a change in the live harmony source. In that situation, there's a very brief moment where Harmonize has forgotten the old root pitch class and has not yet identified the new one. However it happens, if Harmonize doesn't know the root pitch class, then it has no information about how to transpose or conform the input note. So it doesn't. Instead, it plays the input note unchanged. The code also handles a second special case, where Harmonize has identified the root pitch class, but hasn't finished building its harmonization plan. In particular, if it hasn't decided the best output chord factor to play for the scale degree of our input note. I don't see how that can happen, even if Harmonize is responding to multiple messages at the same time. But if it does happen, Harmonize has enough information to transpose the note, but not enough to conform to the harmony. So Harmonize identifies the scale degree of the root note and transposes the input note by that amount. With this input note and root note, the output note is C4. Wait a minute. We wanted to play a note in the same octave as the input note. That octave begins at the octave tonic note, G2. C4 is more than an octave above G2. For some reason, in this special case, Harmonize never even consults the octave tonic note. Another defect, I suppose, but like I said, I don't think this scenario can actually happen. Now we know everything there is to know about how Harmonize handles note-on messages from its input. The last two kinds of messages, note update and note off, are much, much simpler to handle. A note update message tells us that something about an active ongoing note has changed. For example, suppose a keyboard player is holding down D3 and presses a little harder on the key. That sends a pressure change message. I don't know all of the different kinds of MIDI parameters that might produce update messages like this. I do know that Harmonize handles all of them in the same way. The first step is to look up what output note Harmonize is playing for that input note. For that, it uses the table that it updated when it finished processing the note-on message for the note. It simply looks at the row of the table associated with the input note and finds the output note, if any, that Harmonize is playing for that input note. Finally, Harmonize forwards the message to the output note in the same way it did for the note-on message. It simply replaces the note number, leaves the rest of the message unchanged, and sends the message to its output to be sent to the devices that follow. If for some reason the input note isn't active, Harmonize does nothing. Note-off messages at the input are handled in the same way as note-update messages, with one additional step. Harmonize looks up the output note in the table, replaces the note number in the message, retaining other information, such as channel number and release velocity, and sends the message on. Finally, Harmonize records that the input note is no longer active. And there you have it. That is everything I know about how Harmonize works. If you've watched this video all the way through, you are now one of the world's leading experts in how Bitwig's Harmonize device works.